Welcome back. You've just learned how Markov decision processes can be used to determine an optimal sequence of actions for an agent in a stochastic environment. And that is, an agent that knows the correct model of the environment can navigate, finding its ways to the positive rewards and avoiding the negative penalties. But he can only do that if he knows where the rewards and penalties are. In this unit, we'll see how a technique called reinforcement learning can guide the agent to an optimal policy even though he doesn't know anything about the rewards when he starts out. For example, in the 4x3 grid world, what if we don't know where the +1 and -1 rewards are when we start out? A reinforcement learning agent can learn to explore the territory, find where the rewards are, and then learn an optimal policy, whereas an MDP solver can only do that once it knows exactly where the rewards are. Now, this idea of wandering around and then finding a +1 or a -1 is analogous to many forms of games, such as backgammon. And here's an example. Backgammon is a stochastic game, and at the end, you either win or lose. And in the 1990s, Gary Tesoro at IBM wrote a program to play backgammon. His first attempt tried to learn the utility of a game state, U of S, using examples that were labeled by human expert backgammon players. But this was tedious work for the experts, so only a small number of states were labeled. The program tried to generalize from that using supervised learning and was not able to perform very well. So, Tesoro's second attempt used no human expertise and no supervision. Instead, he had one copy of his program play against another, and at the end of the game, the winner got a positive reward and the loser a negative. So he used reinforcement learning, he backed up that knowledge throughout the game states, and he was able to arrive at a function that had no input from human expert players, but still was able to perform at the level of the very best players in the world. He was able to do this after learning from examples of about 200,000 games. Now, that may seem like a lot, but it really only covers about 1/trillionth of the total state space of backgammon. Now, here's another example. This is a remote-controlled helicopter that Professor Andrew Ng at Stanford trained using reinforcement learning. And the helicopter, sorry, I made a mistake. I put this picture upside down because, really, Ng trained the helicopter to be able to fly fancy maneuvers like flying upside down. And he did that by looking at only a few hours of training data from expert helicopter pilots who would take over the remote controls, pilot the helicopter, and those would all be recorded. And then you would get rewards from when it did something good or when it did something bad. And Ng was able to use reinforcement learning to build an automated helicopter pilot just from those training examples. And that automated pilot, too, can perform tricks that only a handful of humans are capable of performing. But enough of this still picture. Let's watch a video of Ng's helicopters in action. Let's stop and review the three main forms of learning. We have supervised learning, in which the training set is a bunch of input-output pairs, x1, y1, x2, y2, etc., in which we try to produce a function y equals f of x, and so the learning is producing this function f. Then we have unsupervised learning, in which we're given just a set of data points, x1, x2, and so on. And each of these points maybe has many dimensions, many features. And what we're trying to learn is some patterns in that, some clusters of these data. Or you could just say what we're trying to learn is a probability distribution for what's the probability that this random variable will have particular values, and learn something interesting from that. And in this unit, we're introducing the third type of learning, reinforcement learning, in which we have a sequence of action and state transitions. So a state, an action, a state, an action, and so on. And at some point, we have some rewards associated with these. So there's a reward and maybe not a reward for this state, and then another reward for this state. And the rewards are just scalar numbers, positive or negative numbers. And what we're trying to learn here is an optimal policy. What's the right thing to do in any of the states? Let's show some examples of machine learning problems, and I want you to tell me for each one whether it's best addressed with supervised learning, unsupervised learning, or reinforcement learning. And the first example is speech recognition, where I have examples of voice recordings and then the transcripts into written text for each of those recordings, and from them I try to learn a model of language. Is that supervised, unsupervised, or reinforcement? Next example is analyzing the spectral emissions of stars and trying to find clusters of stars into similar types that may be of interest to astronomers. Would that be supervised, unsupervised, or reinforcement? The data here would just consist of, for each star, a list of all the different emission frequencies of light coming to Earth. Next example is lever pressing. So I have a rat who's trained to press a lever to get a release of food when certain conditions are met. Is that supervised, unsupervised, or reinforcement learning? And finally, the problem of an elevator controller. Say I have a bank of elevators in a building, and they have to have some program, some policy to decide which elevator goes up and which elevator goes down in response to the percepts, which would be the button presses at various floors in the building. And so I have a sequence of button presses, and I have the wait time that I'm trying to minimize. So after each button press, the elevator moves. The person waiting is waiting for a certain amount of time and then gets picked up, and the algorithm is given that amount of wait time. Would that be supervised, unsupervised, or reinforcement? The answers are that speech recognition can be handled quite well by supervised learning. That is, we have input-output pairs. The input is the speech signal, and the output is the words that they correspond to. Analyzing the spectral emissions of stars is an example of unsupervised clustering, where we're taking the input data. We have data for each star, but we don't have any label associated with it. Rather, we're trying to make up labels by clustering them together, giving them to scientists, and then letting the scientists see, do these clusters make any sense? Lever pressing is a classic example of reinforcement learning. In fact, the term reinforcement learning was used for a long time in animal psychology before it was used in computer science. And elevator controllers is another area that has been investigated using reinforcement learning. And in fact, very good algorithms, better than the previous state-of-the-art, have been made using reinforcement learning techniques. So the input, again, is a set of state action transitions, and then the reinforcement is, in this case, is always a negative number, because there's always a wait time, and so that's a penalty. We're trying to minimize that penalty, but all we get is the amount of wait time that we're trying to minimize.